So, yesterday we looked at our periodic kind of relationships. We looked at how certain types of graphs can repeat a particular portion of the graph over and over and over and over again, like a wave graph, or one I didn't mention yesterday, but if we think about like a heart rate monitor, I'm sure you've seen them in shows or movies like that, or maybe you've seen one in real life, where they monitor a heart and they kind of beep up and down and stuff. That would also be a periodic kind of relationship, that the same kind of pattern happens over and over and over again. At least you hope it does with the heart rate monitor. You don't want any irregularities. So that is a periodic relationship. Now, today, and there's a number of things that we need to look at today, but today we're going to be doing a little bit of right triangle trigonometry review. The concepts that we're going to be looking at today are things that we've seen in Math 2 and Math 3. Now, trigonometry, and that's what we're getting into with Unit 3, trigonometry is the mathematics of right triangles. So everything that we deal with is based off of right triangles. Eventually we'll get into our unit circles. That is based off of right triangles. Everything that we do is based off of right triangles and the trig ratios that we get from those right triangles. Now, to start out then, we want to review our right triangles. So as a little bit of review of that, we have our right triangle right there. And so in our right triangle, we have our two legs, the sides next to the right angle, and the hypotenuse, which is the one across from the right angle. And that hypotenuse is going to be the longest side of that right triangle. And then one important aspect that we use a lot, and we're going to go ahead and use again, is our Pythagorean theorem. I'm sure this is something that we have seen before. How many of you recognize this theorem? Should be something we've all seen, right? A squared plus b squared equals c squared. It is the relationship between the sides of our right triangle. And this is actually a very, very, very old theorem. And it's named after Pythagoras, though Pythagoras probably wasn't the one that came up with it. But he's given the credit and given him his name. And he was a guy from old Greece. It's one of the old Greek people back from thousands of years ago. So this is a very old theorem, one that is used, and we still use it because it is very useful. That if we have a right triangle, we can compare or relate the sides with that theorem. And just that note, that c value is always going to be our hypotenuse. So we're always equal to the hypotenuse squared. So we have two problems here. We're going to go ahead and do B. For your homework is actually going to be, we're going to do about half the problems in this set of notes that I have. And whatever we don't get to is going to be your homework. So we're going to go ahead and do B, and then A will be your homework. So let's go ahead and set up our Pythagorean theorem with B here. So we are solving for x. So anybody want to help us out? How would we set up that lovely Pythagorean theorem with this that we're given? All right, 7 what? 7 squared. Remember, it's a squared plus b squared equals c squared. So 7 squared plus just 5. 5 square root of 2. But all of that is going to be squared. So we're going to square all of that. And then what is that equal to? X squared, right? X squared. So we go ahead and we square each of those. And this one we're not going to give a decimal answer, so no calculator on this one. We'll use our calculators in a little bit, but this one no calculator. So what is 7 squared? All right, how do we do that one? 5 squared root of 2 squared. It would, but we also have to square the 5. So think about that we would square each of those. So I'd have 5 squared times square root of 2 squared. And like Dean said, what happens to the square root when I square it? Cancels out. So we're actually left with 49 plus 25 times 2. And what is 25 times 2? 50. So we have 49 plus 50, and what's 49 plus 50? 99. So we have 99 equals x squared. And so what is x? X is the square root of 99. Now, normally when we solve within an equation like this, because we would square root both sides when we do that, normally I would say we need a plus or minus, but in this case, we don't. It's just plus. Why is it not minus as well? Any thoughts? Say that again. A length cannot be negative. We're dealing with a triangle here with a side length. Now, later on in the unit, we actually are going to have negative side lengths. But that's going to be when we put the triangle within a coordinate axis. So we put it in like the x and y plane. But this one is not within the coordinate plane. So we don't want it to be negative. If it's attached to the coordinate plane, then you have to base it off of whatever the coordinate plane gives you. But this one is not, so we just do positive. Now, that one can be simplified. If we think about this, that is equal to the square root of 9 times the square root of 11. Let's go ahead and write that. You can also use a factor tree. I'm doing a lot of simplifying of radicals with the Math 2 people. And in that, we can actually square root both of those. What is the square root of 9? So I can simplify that to 3, and then square root of 11 would just stay square root of 11. But that would be our simplified answer there. Again, no decimal on this one. There will be times we want decimal, other times we want no decimal. All right, so that is problem B. That's just a little bit of review. Stuff we've seen before, but that is our review of our Pythagorean theorem. Problem A will be a homework problem, so we will be moving on. But any questions on the Pythagorean theorem? All right, next thing that we want to review from previous courses is, well, our right triangle trig, our trig ratios here. Sine, cosine, and tangent. Now these are trig ratios that we have seen and used before. How many of you recognize this mnemonic, whatever it's called, SOHCAHTOA? How many of us recognize that? Heard SOHCAHTOA before, yeah. All right, SOHCAHTOA. Standing for sine, S-O-H, sine is opposite over hypotenuse. Cosine, C-A-H, cosine is adjacent over hypotenuse. And TOA, tangent, T-O-A, tangent is opposite over adjacent. And that comes straight from our right triangle again. All this with right triangles. So when we do our trig ratio, we have our angle that we're going to be looking at. It's going to be based on the location of the angle. Across from that angle is going to be the opposite side. Next to that angle is going to be our adjacent side. And then across from the right angle is always the hypotenuse. Hypotenuse will be right there. Adjacent, the word adjacent means next to. So it means what it means, right? It's our adjacent side. It's the one next to the angle. That's not the hypotenuse, right? The hypotenuse is technically adjacent as well, but it's already special. It's already the hypotenuse. So it's not going to be the one we label adjacent. All right. So let's go ahead and use that. We're going to do problem A here. So we like having our trig ratios because the Pythagorean theorem, as great as it is, requires us to know two of our side lengths already. But what if we don't know two side lengths already? Well, then the trig ratios become handy, especially if we know one of our angles. So this one, we're not solving for all the missing parts. That is a type of problem I could have you do. We're not going to do that here. All the missing parts would be angle B and our hypotenuse and x, but we are only looking for x. Now for this one, we want to use a trig ratio. So which one would we use? We're given this side and this side. Would I use sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, or tangent, opposite over adjacent? Discuss it in your group. Which one would you use and why? So would this be a tangent, sine, or cosine problem? Orlando, what did your group discuss? Is this a sine, cosine, or tangent problem? Why? O and A, right? So we have from 56. Let's actually do this first. What is the side opposite the right angle? That's a hypotenuse, right? So automatically, this is our hypotenuse always. So from 56, this would be opposite, and this one would be adjacent. And we can go ahead and throw that in. So the way we write it, we're using tangent. Tangent of what? So this is a function. Our trig function, sine, cosine, tangent, and later on we'll have secant, cosecant, and cotangent. All of these are functions, just like our logarithms. When we did logarithms, did we just leave log by itself and say log equals 2? Would this be correct? Or are we missing something? What are we missing? We have to ask ourselves, log of what equals 2? Right? Because we need an argument. Log of what equals 2? If you just have log, that means nothing. You have to have log of something. Same thing with tangent, sine, cosine. It is a function. So tangent of what? What goes inside? Well, let's go back. Tangent of, does anybody know what this is? Not 0, that's a little line. It is the angle. This actually, let me write this down. This represents the Greek letter theta. Theta. And theta and other Greek letters such as alpha, that's alpha, beta, all of these are Greek letters that we use to represent angles. Okay? So often we'll say sine of theta or tangent of alpha or something along that lines. Now, often we'll also use capital letters, but we often will use the Greek letters to denote angles. So if we are doing tangent of theta equals opposite O over A, what is our theta? The 56, not the 90. It'll be the 56. 56 equals, what are we given as our opposite side? 12. And our adjacent side? That's where our x goes. And we are solving for x. So how do we solve for x? Any thoughts? We will use a calculator eventually, not yet. Okay, so we want to multiply both sides, but I wouldn't say 12. What is that? x, because it's the one in the denominator. If I multiply by x, that would give me x times tangent of 56 equals 12. So we're wanting to solve for x, so what can I do now? Divide by tangent of 56. Tangent of 56 is just a number. We'll figure out what number in a moment. But we have tangent of 56. I like to use the parentheses there to indicate that the 56 is being plugged into my tangent function. So x is equal to 12 divided by tangent of 56. Go ahead and pull out your calculators and see if you can plug that in. All right, so there are two answers probably out there. How many of you got like negative 19 point something, something, something? Okay. Did anybody get 8.094? Okay. Which one is correct? Now think about this. Logically, can the length be negative? We talked about this earlier. Can the length be negative? So which one logically should it be? But why is your calculator giving you the other one? It's because you're in the wrong mode. So we have to pay attention to that. See, even mine, look at that. It gets chunks out both. You have to be in the correct mode, regardless of what calculator you have, whether it's one of these, your phone, anything like that has to be in the right mode. We have two different types of angle measures. Degrees, which we're familiar with, and radians. We will be talking more about radians tomorrow. And this course is actually going to be primarily, if not all, entirely in radians, not degrees. So how do you change it? Well, you go to mode. Right here, the one I have in red. Mode. And look, mine is on degrees, but I can switch it back to radians. So you have to be in the correct one. All of you that got negative 19, your calculator was in radians, not degrees. So you have to switch it to degrees and then do it again. Now Casio, yours will be in the setup button. If you go to run and then setup, you can change the angle as well. So for this problem, we should be in degrees, not radians. So switch to degrees. Now at the end of the class period, those of you using my calculator, I want you to switch it back to radians. But for right now, we'll be in degrees. And the reason why is that everything that I do, we're going to be doing in pre-calc. Everything I do in calc is all in radians. I don't use degrees at all. Okay? So I want all my calculators back in radians. So if you switched one of mine to degrees, switch it back to radians at the end. All right, but you should be getting 8. The top one was in degrees. This bottom one was from radians. So 8.094. All right, so let's go ahead and write that in. The correct answer, 8.094. My thing will do what it's supposed to. 094. Okay. Any questions? All right, problem B is going to be yours for homework. Same idea, using a trig ratio. Now, the other thing that we're looking at is inverse trig functions. Inverse trig functions are the ones that allow us to find angles. Well, if I have tangent of theta equals, and we just used this was equal to opposite over adjacent. Well, if I wanted to know what my angle was, I would use the inverse. And that would be opposite over adjacent equals the inverse, tan inverse of the angle. Actually, no, that's wrong. Sorry. Woo. The angle equals tangent inverse of the opposite over adjacent. Sorry about that. That was confusing. That is correct now. I was like, wait, that looks wrong. So the regular trig function, the argument inside is an angle. In the inverse, the result is an angle. We're looking for the angle. So this is a way we can solve for the unknown angle. And we write it as either tan inverse, so the little -1 is an inverse. That should look familiar because we've used inverse before. Does that look familiar? F inverse? Should, because we've used it already this year. So it's the same idea, it's just the inverse. Or we can also use arctan. So this would be equivalent to arctan of that O over A. Okay? Both of them mean the same thing. Arctan, tan inverse, or arcsine, sine inverse, arc cosine, cosine inverse. They can be used interchangeably. So let's go ahead and do problem C. This one, we're given two sides, so theoretically I could use the Pythagorean theorem to find the third side, but that's not what they asked me to do. They want me to find the angle. So this one right here is our unknown angle. I'm just going to go ahead and use theta on that. All right, looking at this in your groups, decide, is this a sine, cosine, or tangent problem? So which one is it, guys? Sine, cosine, or tangent? Why sine? We have opposite and hypotenuse, so that would be correct. Sine of theta is opposite over hypotenuse, so sine of theta equals 7 over 16. So how do I get theta by itself? What do I write? That's what I'm looking for. Theta, my angle. What do I write? What's the opposite of sine? The inverse sine, right? Or sine inverse or arc sine. So if I'm wanting to undo sine, I use the inverse, sine inverse of 7 over 16. Now you're going to input that into your calculator. So where do you find the inverse? They're right above your trig function. So look for your button for sine. Right above it, on the TIs it should be in yellow. Right above it is the sine inverse. So we see that right there. Oh, it's not in yellow, it's in blue. So right above my sine is sine inverse. Right above cosine is cosine inverse. Right above tangent is tan inverse. So I would do second. Casio, same thing. It's right above the trig function. And then I do 7 over 16. So input sine inverse. And again, should be in degrees. We want a degree measure for this angle. All right, what are we getting for our angle? Anybody want to share what they got? 25.944 degrees. This is a degree, so we need to put the unit of measure. That's going to be very important. Again, starting tomorrow when we start looking at radians. So degrees. All right. So problem 3 and 4, we don't have time to do those. I want to get to some of the stuff on the back. Maybe if we have time. Problem 3 and 4, I highly recommend drawing a picture to show what's going on. So this one we have a surveyor standing from a very, very detailed tree 50 meters away. We are told the angle of elevation to the top of the tree, so that's this, is 71.5, and we want to know the height of the tree. What is the height of the tree? Well, now we have a right triangle. Wouldn't this just be another right triangle trig problem? We have an angle. We have two sides. Well, one side. We want to find the other side. We would just use a trig. All right, to finish this problem, we would look to see what trig ratio we would be using. And this one is another tangent because we have our opposite side which is our unknown, which we can label as x, our opposite side, and our adjacent side. And so we would have tangent of 71.5 equals opposite over adjacent. And then we would just go ahead and multiply 50 to both sides, and x is equal to 50 times tangent of 71.5. If you plug that into your calculator, we get 149.434 feet. And that would be the height of the tree. So again, problem 4, in a very similar manner, draw out a diagram and then use a trig ratio to use it. I believe on that one you're looking for the angle, so you're going to have to use an inverse trig. So on the next page we have our trig ratios. The ones we are familiar with, we've been using just a little bit now, are cosine, sine, and tangent, SOHCAHTOA. And then we have these three, which should be a little bit new. Some of you may have seen them before, but these are what we call our reciprocal trig functions. These the reciprocal trig. Not the inverse. These aren't inverses. These are reciprocals. And hopefully we can see that if we have cosine, cosine is adjacent over hypotenuse. Well, if we do, this is called secant. If we look down here, I have what each of these are. This is secant. So secant is the SEC, cosecant is the CSC, and cotangent is the COT. And these again are our reciprocal trig functions. And if we know one, so say I know cosine adjacent over hypotenuse, to find secant, all I need to do is reverse what we have. Notice this is hypotenuse over adjacent. And so if we know, say, cosine of theta is equal to 1/2, then secant of that angle is equal to 2 over 1, the reciprocal. And the same thing for sine to cosecant, tangent to cotangent. So cosecant is the reciprocal of sine, cotangent is the reciprocal of tangent, and that's actually what this means right here. It means that they are reciprocals of each other. All right, so in problem number 5, we have our triangle right here. We have triangle ABC, and we want to find these, 9 different trig ratios here. So starting with sine of A, and this is again very important, what angle are we looking at? Angle A, sine is opposite over hypotenuse. Well, what is my opposite side from A? That would be 16. So 16 over 34, which could be reduced if we wanted to. Now that I have sine of A, I can know its reciprocal, cosecant. So let's see if they ask me to do cosecant of A. Here's a cosecant, but that's cosecant of C. So I'm not going to do that one yet. I don't see cosecant, but cosecant of A would be 34 over 16. Let's go ahead and do this one here. I'm going to use a different color for angle C. So this one is cosine of C. So that's from here. So that would be adjacent over hypotenuse. Adjacent would be 16 over 16 over 34. Which, notice, is the same value as sine of A. They actually are equal to each other. That's a property of complementary angles there. Well, I have cosine of C. Let's see if we can find its reciprocal, secant of C. Do they ask for secant of C? I see a secant, but that's secant of A. No secant of C, but secant would be 34 over 16. This is cosecant. Let's actually do sine of that first, which is right down here. So here is sine of C opposite over hypotenuse. From C, my opposite side is 30 over 34, which could be reduced. And then when I want to do its reciprocal would just be that flipped, 34 over 30. So when we find that reciprocal function, we just flip the one that it comes from. Tangent, let's go ahead and do tangent. Tangent of A, so we're back to angle A. Angle A, tangent opposite over adjacent, opposite, adjacent. So that'd be 16 over 30, which again we could reduce. See, do we have cotangent of A? No, we do not. We have cotangent of C, but cotangent would be 30 over 16. Cosine of A. Let's see, cosine of A, we're back to, nope, still angle A. I was thinking I was going to the next one. Cosine of A would be 30 over 34, our adjacent and hypotenuse. 30 over 34, which again could be reduced. Let's see, do we have secant? Yes, we do. Right here, secant of A would be the reciprocal of that, 34 over 30. All right, and then we have tangent and cotangent at C, so let's do tangent first at C. Tangent would be opposite over adjacent, so that would be 30 over 16, and then the reciprocal would be 16 over 30. Again, all of that could be reduced, but that would be those trig ratios. And again, paying attention to which angle we are looking from. All right, let's go ahead and do problem 6. So problem 6 here, we are given a trig ratio and we want to find the other 5, so it's 6 total. So we know sine of theta is equal to 2/3. We want to know what is cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. Now, one we can already know just with what we know. Which one is that? That would be cosecant, right? Because these are reciprocal. So if sine is 2/3, then cosecant would be the reciprocal 3/2. All right. Now, to do the other ones, though, we need more information. So we're going to actually go into our triangle. So this requires us to build a triangle with the information we're given. We're going to say our angle theta is here. And using sine being opposite over hypotenuse, opposite hypotenuse, that'd be 2 and then 3. Now, to be able to do the rest, cosine, tangent, and all the rest, we need the adjacent side. So that means we need to solve for that adjacent side there. But to do that, we just use our Pythagorean theorem. So x squared plus 2 squared equals 3 squared. And that would give me x squared plus 4 equals 9. X squared equals 5. And x is equal to the square root of 5. So now I know my adjacent side is the square root of 5. And now I can fill in the rest. Cosine adjacent, square root of 5, over hypotenuse 3. And now that I know cosine, I can figure out secant, the reciprocal 3 over square root of 5. Tangent is opposite over adjacent, so opposite 2 over adjacent rad 5. And now I can find my reciprocal cotangent by flipping it, rad 5 over 2. And that is how we could find our trig ratios based off of just one given. Now for problem B, that will be your homework, but I do want to make a note here. If we have cotangent, remember that means we can also know tangent. So if we know cotangent is 3/4, what would be tangent? That's right, it would be 4/3. And you would build your triangle based off of the 4/3. Opposite and adjacent, right? Well, that's going to conclude this video. Again, remember your homework will be the rest of the problems that we didn't get to. Thank you for watching.